This episode is brought to you by Calcbook.
If you've ever spent hours digging through spreadsheets for errors or used software that spits out results but hides the math, you've probably thought, there's got to be a better way.
Calcbook gives structural engineers transparent, line-by-line calculations in a clean, user-friendly interface so you can trust your results and work more efficiently.
Listeners of the Structural Engineering Podcast get 50% off their first 3 months at calcbook.com with promo code SEPOD. All capital, all separate letters. We'll put it in the show notes.
Calcbook, calculations done right. Welcome back to the Structural Engineering Podcast. In this week's episode, we're joined by Ryan Musgrove from Kramer Gehlen Associates to talk about one of the most efficient and elegant systems in structural design, post-tension concrete.
Ryan walks us through the fundamentals of PT design, the advantages it offers over conventional reinforced concrete, and some of the challenges engineers face in detailing and construction. We also dig into the design philosophies, field coordination, and how PT can help reduce material waste while maintaining performance. Whether you're just starting to learn about post-tension systems or have designed dozens of slabs and beams, this episode has something for you. Let's dive in.
The Structural Engineering Podcast.
I'm so glad it's recording.
The gag reels, right? You guys have that on your yeah.
Well, thanks, Ryan, for being on the Structural Engineering Podcast. As we start, you want to give a little introduction of yourself?
Yeah, thanks for having me. It's we've been talking about it for a while doing this, and we have history. We've worked together in the past, and I've known you since. Actually, I forgot you. We came to a class you were at when we were in school, and we talked about what we do at Kramer Gehlen, where I work, and you ended up coming to work with us for several years, and it was a good experience. And so, yeah, we can stay in touch, and it's good to do this. So.
Yeah, I'm excited to talk about post-tension with you today. But
Yeah.
before we get into that,
Yeah.
where do you go to school? What does your career look like?
So I grew up. We're out here in Southwest Washington. So I'm born and raised my whole life. Went to Washington State. Got my undergraduate and my master's there. Worked on post-tensioning. In my research for that, we actually did thermal testing of ducts, and we can get into that later, but looking for voids in grouted ducts using thermal cameras to see if we could see voids. And so that's my first exposure to kind of like post-tensioning besides the post-tensioning class we had. So came to work after I got my master's, came back to the area and came to work for Kramer Gehlen, and I've been here ever since. This July 26th will be 20 years. So, yeah. And like I said, in that time, then we met and stayed in touch. And that's kind of where I got my start with post-tension. Kramer Gehlen, I've worked on a lot of projects over the years in the area. And so that's basically, as a designer, you get thrown in and said, hey, you're going to figure out how to do this.
Yeah.
So that's what we did. So.
That's pretty awesome. Well, we're here today to talk about post-tension. So can you give us a quick overview of what post-tension concrete is and why it's used?
Yeah, I mean, mostly for our projects in our area, we use post-tensioning. So it's concrete, instead of just being conventionally reinforced concrete with rebar, we have post-tension strands inside the concrete that get draped to create profiles to help balance the load. Basically, you counteract the moment diagram of a slab, and so you have this parabolic shaped tendons that flow through the concrete slab. We typically do flat plate slabs.
What is post-tension concrete and why is it used?
Post-tension concrete, yeah, we use concrete slabs that have post-tension cables. They're high-strength steel cables that we stress in these slabs that help minimize the depth, because you actually counterbalance the dead load that's on the slab, on all the load, but really we focus on the dead load balancing. So we can use those tendons, and we put a stress on the end of them. We tension those cables to around 33,000 pounds each. And this is an unbonded system, typically what we use.
What are the material breakdowns of PT? So you got the tendons, the rebar, and then what are the elements of PT? Like you do them in slabs, beams, columns, brace frames, whatever kind of thing.
Sure.
So
yeah.
There's a lot at you right now.
Basically, our office, we do PT slabs out here for residential, multifamily projects. We do high rise. We've worked on podium slabs, like 5/2. We have wood frame on top of the slabs. Anyway, the post-tension slabs are concrete slabs that have post-tension cables profiled throughout their thickness to help balance the dead load that's on the slab. And so we use these post-tension can be used in slabs, can be used in beams, they use them in foundations. And these cables are draped through the concrete slab, and then they're stressed to an effective stress, basically on the ends, using hydraulic jacks. And we pull those cables and put a force in the cable that gets imposed into the concrete slab to help thin the slab, make more effective sections, and get longer spans.
So, is there any value? I'm thinking through concrete class and cracked concrete and things like that. Now I'm thinking we're stressing it. Does post-tension slabs or PT help with the cracking in those elements?
It does. And so really when we design a post-tension slab, we are designing it for an uncracked concrete section. And so when you have a cracked section, you lose effective inertia on that slab section. So when we impose that pre-stressing force into the slab, it holds the section together and balances it counteracts the tensile stresses in the concrete. And so that way, when we look at the section, we can say it's a uniform uncracked section versus having to take a reduction in overall inertia, which helps with our deflection checks and for serviceability.
That makes a lot of sense. So, tell me about the grades. What grade of steel, strands, concrete are you typically using for these?
So our concrete strengths, around in our area, we're typically using around a 5,000 PSI concrete strength. And we also try to look for a low shrinkage because inherently concrete's going to shrink. And then when we add a post-tension force onto the slab and compress the slab, it's going to amplify the shrinkage. And so we want to minimize the shrinkage as much as possible. So we look for low shrinkage mixes. We use rebar that's typically around a 60 KSI still for our rebar, for our mild reinforcement. Our strands, the steel strands, are 270 KSI 7-wire strands that we use. And those cables, they have a really high yield strength. And so there's less effective loss because when those strands relax over time because of the sustained tension on them, it's what is used in industry today. So,
for any of our younger listeners, what is low shrinkage concrete? What do you look for to make sure that it is low strength or low shrinkage, not low strength?
Well, we try to minimize the amount of water. We look at aggregate size.
So Ryan, what types of projects are most common for PT concrete? Are there any surprising applications people might not be thinking about?
Most commonly in our area, you see that on multi-story projects. The biggest benefit for post-tension concrete we talked about earlier is the ability to have longer spans and thinner sections. If you take, say, a steel building with concrete over metal deck, your floors, you may have 10-inch, 12-inch joists, 18-inch girders, concrete topping, 3-inch metal deck and some topping on that, versus the typical post-tension slab for a residential floor in our area could be 7 or 8 inches. So when you're building a residential type building, you can get more floors, more square footage, and you have more units that you can sell because you lose that assembly thickness. And so with our thin slabs, we see a lot in residential. We also see those slabs used, and like I said, podium slabs. A podium slab, basically, we build 1, 2 floors of concrete, and then we call them 5/1s, 5/2s, 4/1s, 4/2s. So basically, you have 4 stories of wood frame sitting on top of basically the foundation that's actually the PT concrete slab. Those slabs are thicker because they have to carry this heavier sustained dead and live load. So they could be 12, 14, 16 inches thick. But we say that a lot in our area because there's a lot of multifamily mixed use projects where you'll have retail on the lower levels and a concrete level, and then we'll have residential above. And so it works well. We'll have parking below as well sometimes. So we have a concrete layer, then we switch to the wood frame structure above because the wood frame works well for the cost above. And so we basically use that podium slab as a foundation. So we anchor our wood hold downs from the shear walls, all the sill plate bolting, everything gets anchored into that slab, and then that's used as like the foundation. The PT slab transfers the load then down to the foundation.
So diving in a little bit more technical, what are the main structural advantages of PT over reinforced concrete? And, thinking, I'm going to take a guess that it's going to make the slabs thinner from stuff you've already said. How much thinner than a more traditional, conventional framed reinforced concrete building?
Well, from my experience, like I said, typically we're going to have some spans. We can get longer spans. The biggest thing is we get longer spans with thinner sections. So instead of being somewhere about a 14, if you just did a flat plate concrete, conventionally reinforced concrete slab, maybe we're looking at 14-foot, 16-foot span, something like that with a conventional reinforcement. For a similar thickness, we may be at 26, 28 feet with post tensioning. I mean, with a good column layout, we can usually get somewhere between, and that number grows, and then it also affects the slab thickness, but we can get in the range of 7-8 inch thick slabs for a residential floor, where, like I said, and that's almost 50% more span length.
Do you have any ideas of, like, from a cost perspective, conventional reinforced concrete versus post-tension concrete? If, like, not necessarily $1 a square foot, but like, is PT 1.2 times the cost, or do they offset each other with having thinner slabs?
There is less material, but then you do have the installation of the post-tensioning. I know there is a premium on that. We don't get into a lot of the costs the cost right now. There's a lot of volatility in construction costs right now we're seeing. So I don't have an exact percentage. It's usually going to be more expensive. I mean, there's the extra labor you have for stressing the tendons. There's usually teams that install these cables. A lot of the construction companies around our area are familiar with post tension. It's very popular in our area. But there is somewhat of a premium. I don't know per se dollars per square foot, like I said now, because of the volatility and the pricing. But there is a little more expense with that, but durability, long-term performance of the post-tension usually balances out. And plus, the biggest thing is that you can get, like I said earlier, is the savings on the profile section, the section thickness of the floor assembly. So usually the expenses can be recovered because of the efficiency of adding extra floors or so forth on the building. So.
Okay. No, that makes a lot of sense. Now, you talked about something about maybe the tendons relaxing or something like that. So how do you approach balancing the pre-stress losses in your design?
Without getting into all the technical parts of the slab design, basically we know there's going to be a dead load and a live load on the slab. And so our goal is to help balance a percentage of that dead load with the post-tension tendons in the slab. And so when we model our tendons, the tendons usually come through in like a parabolic shape. And when we profile those, they're to basically balance the deflection of the dead load that's already on the slab. And so we look at like a ratio or percentage of like 80 to 100% dead load balancing would be good. Sometimes it's over that. It ends up being that way depending on the loading condition. Mm-hmm. Is it a podium slab? Does it have a big heavy planter that's got 4 feet of soil in it? Or is it just a residential floor? And so we try to be in that range because the slab performs the best we found in that area. If you get too much post-tensioning in the slab, you can actually cause excessive shrinkage, and you guys also get uplift in the slab, because if this tendon is draped, you're going to cause an inherent uplift in the middle of the span of the slab. And when that happens, you can actually crack the slab on initial stresses when you first stress the slab without the dead load being on the building. So you have to think through that process. Sometimes with beams we've had in buildings where we have columns that don't stack as they come down the building, we have a beam and we have a transfer beam where the column sits in the middle or somewhere along the span length of the beam, and then we'll do what they call stage stressing. So we know that this beam could be, I had a project where we had a beam that was 40 feet long over a drive aisle, and it had a column that was carrying like 15 stories of a building above it. And so it ends up in the middle, this beam 6 feet thick or deep, and about the same, about square and cross section, and it had over 100 tendons that was used to balance that overall load that would be sustained on the building. And so if we stressed all 100 tendons at one time, that beam would basically blow up because it had no load on it at the time of loading. So we had to figure out, all right, we're going to build the beam. Let's put a minimum amount of pre-stressing in it. Build 3 floors of the building above, keep it shored, and then stress, say, X amount of tendons. Then, all right, let's build 3 more floors, stress X amount of tendons until we get the dead load we anticipated on the slab. Because if you overestimate your dead load and you put too much pre-stressing in the slab, you can get issues, especially around, let's say, on the perimeter. We've seen where, say, you have cantilever decks and you lift on the deck too much with too much pre-stressing, you can actually have the decks curl, and because there's less, and if you overestimate the load that's actually on the deck doesn't settle down as you anticipate, and you end up with curling where if it rains and the water runs back to the door of the threshold, and that's not an ideal situation. So we want to make sure that we really take a lot of pride in reviewing the balancing dead load, deflections, so forth, to make sure that the slab ends up in the final state with the load that we anticipate at the right locations.
So it really sounds like it's an art form. I mean, more than there's science, there's engineering behind it, but like someone that's done it for a long time is probably pretty good at knowing where it should be and how it should kind of.
Yeah, we joke about I'm not the smartest guy. I'm not the PhD. I've worked with PT slab. I've designed a lot of slabs for our company. I've been fortunate enough that we've had a lot of inherent institutional knowledge because our company has been around for over 50 years. And so it's been a lot of people that have taught me and helped me along the way to learn how to do PT slabs, in addition to having some classes, in college. But the actual in-field training and learning, like you go out to the site, look at how it's actually built, and then bring that knowledge also back to the office for when you do your analysis, is really important. It's been very valuable. And so there is somewhat of an art for me. Now I know here's our layout, here's a new building, here's our column layout. What do you think it's going to need for a slab thickness? And that comes just with experience, but like, oh, we're going to be 10 inches here, probably need a 12 inch, we're going to thicken it in this area. It's just things you learn over the years. We're going to need this much PT here. Start with this 200 PSI. And I say 200 PSI, that's the average compressive stress in the slab due to the post-tensioning. So the code minimum is 125 PSI. We never want to design our slabs to 125 PSI of pre-compression, because if we do that and say for something happens, and we can talk about later with construction issues, something happens with tendon, you lose a tendon. Now, if you lose a tendon and you're at 125 PSI, you drop below code minimum. So we never try to strive for that value, but like a good efficient slab, you'll read in a lot of literature and technical documents, if we can stay around like a 200 PSI effective stress in the slab and still make our stresses and work for the slab, it's a great design. Sometimes we have to go higher. Sometimes we're at 300 PSI. We've had things at 400 PSI, beams and so forth. Sometimes they're even higher in beams, but those elements are tied, try to hold everything together. But you have to think about the more pre-compression we put into that slab, the more shrinkage we get. And so by doing so, we have to just think about the big picture. It's like, all right, this slab's going to shrink more. What are our restraints? Where are our walls located? Just for laying out that slab, so we don't have to try to minimize the cracking as much as possible.
Yeah. So going back to the podiums, I'm just thinking out like how you balance things in your stage stressing.
Yes.
When you have a podium structure and you have 4 or 5 stories on top of it.
Yes.
You're adding dead load through the construction. Podiums, from what I've seen, are a lot thicker. They're transferring a lot more different and more loads.
Correct.
Are those stage stressed, or how does that work?
Typically, we don't stage stress there's lots of ways to do podium slabs, and just one person, one company, but they typically, you wouldn't see stage stressing on a podium slab. They can vary. They are thicker than a typical residential floor. There have been instances where we've stage stressed a few locations that had thicker regions, or we have extra tendons or so forth, or a lot of dead load. But typically we try to avoid that, because then also the crew has to come back, and it gets into the construction part of it. But you also have to have a special inspector on site to measure the elongations, because you pull on these tendons. We use an unbonded system typically around here, which is the cable is wound through a greased plastic sheath that gets draped through the profile of the concrete slab. And that tendon, as you pull on it with a big hydraulic jack, you pull the tendon, and you have to measure an elongation, and that gets calculated by the PT supplier. They usually will do the elongations. We can do those around here. Typically we get deferred submittals where profiling the tendon count, and then the losses, as you mentioned before, are also they're calculated. They give an elongation that we should see in the field, and we verify those elongations too, along with special inspectors.
Okay.
So I think
So you brought up bonded. What is the difference of bonded and unbonded tendons? Differ in design, long-term performance? How does that work?
As far as the design of a bonded system, I don't have a lot of experience in doing that. It's not a very common system for what we do in our office with residential slabs and so forth. We have worked on bonded projects. I have colleagues that have designed bonded tendon systems. And basically the difference is that, as I said earlier, ours is an unbonded system. So from one end of the slab, whether it's 100 feet, 200, 400 feet, this cable, there's individual cables that come out in their typically half inch diameter strands, or wound cables that drape through the concrete section, and you anchor them. They have heads on the end that are attached to the cable. And so we call them stressing heads, or so with an unbonded system, we have a stressing head end and a dead end, we call it. And so sometimes there's a certain length of tendon that you can, and this gets into further into the design, but you have losses. This cable is inside this post-tension cable is inside a plastic greased sheath that slides inside the plastic. But the forces, the pre-stressing forces, are imposed on the far ends of the slab. There's on an anchor end on one end, and there's a stressing head on the other end. It has a steel head on it that you actually put the hydraulic jack, and you pull on the cable inside. It pulls through the plastic sheet, imposes the pre-stress force into the concrete slab, and that's how and then that gets anchored off, and then the pre-stress force stays in the concrete slab with an anchor. With a bonded system, we have plastic, they call them ducts. They used to be metal, and then now they use plastic, typically poly of some kind of a duct. And they have ribs and so forth on them that actually bonds to the concrete. And then the ducts usually have several tendons inside, and those run from end to end as well. And then you stress them. But then and the difference between unbonded versus bonded is these tendons that are inside the ducts then after you stress them, you grout the duct and fill it full of a non-shrink grout. And then you release the anchor, you release the jack, so it loads the slab, but those pre-stress forces actually gets transferred through the grout, through the plastic ducts, and into the concrete slab. So with that system, the pre-stress force is effective throughout the length it's transferred throughout the length of the slab. Whereas an unbonded system, it's greased smooth. There's no force transfer throughout the length of the tendon. It's only on the ends of the slab. So one possible downfall of a unbonded slab is that if something happens to that tendon anywhere along the length, you lose the effective pre-stressing force along the entire length of the slab. Whereas a grouted system, the forces are transferred along the length of the tendon inside the grouted duct, and that force gets transferred to the slab. So say there's a TI improvement, tendon improvement going on, and you drill into a tendon by accident and you break the tendon. If you break the tendon in an unbonded system, we have to see, well, do we have to restring it, which can be done. It's a lot of work. It's time consuming and expensive. Or with a bonded system, it's more forgiving. We still don't want to actively say it's okay to drill tendons.
Yeah.
It's not a good practice. But when we do that, if it does happen, those forces are locally. You only lose the effective force of the pre-stressing in a couple of square foot area. So
Yeah.
This episode is brought to you by CalcBook.
As engineers, we all want calculations we can trust. But spreadsheets are cumbersome, and traditional tools often feel like clunky black boxes, slow, outdated, and impossible to verify.
CalcBook is different. It's modern, intuitive, delivers professional hand calc style outputs that give engineers real confidence in the design.
Listeners of the Structural Engineering Podcast get 50% off their first 3 months. Just visit calcbook.com. Use promo code SEPOD. That's SEPOD.
Built by engineers for engineers.
So something that came to mind when you were talking about stage stressing and that beam that was 6 foot by 6 foot-ish that was supporting 15 feet. And now talking about core drilling and tenon finishes. You know, in my mind, like one important thing that us structural engineers do is prevent failure from occurring from both, gravity, typical loads, lateral loads that we deal with, but also people going in there and messing around with the structure.
Sure.
So is there anything like that beam or anything else? How would you prevent people from going in there and just cutting it? Because that would be catastrophic. Am I right?
That would be catastrophic on something like a transfer beam in a high-rise concrete building. If you eliminated all of the post-tensioning in that beam, the beam would likely fail. The good thing about post-tension is it's still embedded in the concrete section. We have cover distances. Everything is encapsulated within the concrete. And then the anchors, excuse me, we talk about the anchors. At the ends of the anchors, what the dead ends are not even exposed. They have cover distance with concrete covering those. On the stressing ends, we pull that cable, say on this unbonded system, we pull the cable out, the tail of the cable, we leave extra so they can grip onto it with a hydraulic ram, pull the pre-stressing that we need into those cables. And that's the process we can talk about. But basically during construction, the contractor will stress the tendons, and then they pull them, and then we anchor them. They get anchored off, and then they cut the tendons off, and then there's a grout pocket at the end, at the anchorage, and we actually cover up the tendons to protect them from the environment, from, sabotage or whatever, I guess you want to call, somebody doing wrong. They get covered with grout. So in the end, it looks like a concrete beam. You can only see the difference in color from where each grout pocket is for the stressing ends, but everything is concealed inside the concrete section. So
how often do you hear, or have you been part of projects where they've cut a tendon? Like, is this a really common thing? In my mind, just thinking through other projects that are out there and all the jokes in the industry about plumbers and electricians, like I feel like they're going to just be cutting through the heck out of these cables. Maybe not a transfer beam, but is it pretty common?
It as a structural engineer, I would say it's more common than it should be.
Yeah.
Usually we get calls. Some projects we have great success on how they go. Sometimes trades, for whatever reason, aren't as experienced working around post-tension slabs, and they're like, maybe the guy in the field needs to drill something for some kind of sewer line or whatever it is, a water line, and they start core drilling. There are methods you can try to locate tendons. They have X-ray and scanning tools that you can use to try to find those, but usually these slabs have, like I said, mild reinforcement, maybe in the bottom, a grid, and there's also these tendons that drape through the slab at different profiles, and they can scan to try to find them. Sometimes it's not 100% effective as well, and so it is difficult. And then you get the call that, oh, our plumber drilled through 3 tendons, and now we have to figure it out. So then it comes back to the structural engineer record. We have to review the slab and see, well, we've lost 3 tendons. Typically, that amount is not going to be just something we can say, okay, no big deal.
Right.
Because then you get questioned by the owner, like, well, why were they there? Why did I pay for those tendons? So if that happens, then we have to, like I said, we have to re-string those tendons, and they can actually physically put a new cable through and then re-stress those tendons after the fact, after they've been drilled, and they fix the drill hole, fix the sheath, and then they'll come back out again with the hydraulic ram and pull on it and re-stress it and give us a new stressing report from the special inspector, and then we can sign off on it. Because a lot of times what happens is we find out that the stresses aren't met per code when we lose that effective pre-stressing. And so now we may end up with a crack section when that wasn't what we originally intended. So it does happen. I have friends in the field. I have contractor friends that they make jokes. It's easier to ask for forgiveness than permission. And so they always joke about, those tendons don't mean anything. Your engineers have safety factors, but they do.
Yeah.
We don't want people drilling them, but it does happen. But there are ways to fix them. So with a post-tension slab, it is best if we can try to coordinate those kind of sleeves and things like that ahead of time. And it's critical. And that's one of the biggest things we talk about when we talk with contractors is make sure your trades know where their sleeves are going. Let's do this ahead of time so we're not drilling this slab later, because it could end up in a location where we can't drill through it. And so let's try to not have broken tendons.
What's the my mind just went to I wonder how expensive that is. Is this like a few $1,000s, tens of thousands of dollars, hundreds of thousands of dollars to fix a tendon? What do you feel like is?
I don't think it's hundreds of thousands, but I have heard there was a project recently we had where somebody drilled a tendon, and I think there was a couple tendons where they were drilled, and the contractor made an offhand comment about this is going to be $10,000-$15,000 for a couple of tendons. So definitely not cheap.
Yeah.
And who pays for that? I know the contractor has to work that out, but it goes into the budget of the project. And so someone's got to pay for it, but it does happen. There are ways to fix it, but we try to be proactive to coordinate and be very explicit with our contractors, that don't let your trades, your subs drill holes in our slabs unless it's absolutely necessary, and we've done the best we can to try to locate the best location to drill it.
Yeah. Okay. Could you talk more about, you brought up talking about how they're draped and things like that. Can you talk about the common tendon layouts, banded versus distributed, and when each is most effective?
So our typical tendon layout would be we call it a banded direction and a distributed direction. And what that is, basically you have columns on a flat plate slab design. You're going to have columns at 20, 24, 26, 28 feet on center. And so in one direction, we will group up all the tendons for that tributary region. So basically we say we want that 200 PSI, P over A. So we know effectively after they stress that tendon to 33,000 pounds each, and then they seat it into the anchor, and then there's some shrinkage, there's some steel loss. We end up with an effective force of, let's say 27,000 pounds, 27 kips. So then we can just do a simple P over A and figure out what's our effective stress in the slab. And we shoot for that 200 PSI, 300 PSI, and we figure out, okay, well, I need 40 tendons on this band. We group those tendons side by side, usually in a group, and we call it a banded run. And they're, depending on how many tendons, because each tendon has an anchor that's like 3 inches wide. And so we have all of those tendons draped in one direction. And then in the other direction, we call it the uniform direction or distributed direction. The groups of tendons, 3 or 4 at a time, are spaced, say, every 3 feet on center. And so it's like a grid of tendons in the opposite direction. And we do that. It's just a construction practice. And really it tries to help for construction, for trades, for sleeving and so forth. You could do distributed in 2 directions and just have like a mesh that look like your mesh of rebar in the bottom of the slab. Or you could do a banded direction. I mean, they do allow that as well. But the typical practice is a banded one direction, distributed tendon the other direction. So, and then the same thing, we figure out how much P over A do we need in the slab, and then they figure out how many tendons accordingly. So.
Okay, that makes a lot of sense. What are some of the biggest misconceptions that you've heard from other engineers, maybe your colleagues or others in the field about PT systems?
Well, I can't really speak for other engineers, other than per se in our office. When we get brought into working on PT slabs, at least in my experience, when I started, like I said earlier, our office is a lot of slabs, a lot of post tensioning, whether it's podiums or just flat plate single floor, supporting single floor. And so when I was working, when I started doing PT, there was a job and we had like 20 different slabs we had to design, and they said, go at it. So I started out using a kind of an equivalent frame software. We call it strip modeler for short in our office, but basically you look at one direction, a tributary width, effective frame width, and you design use the software and try to go through and design the slab. And then you go to the next column line over and do an effective width, and you do a design strip. And you can basically do that in both directions for the column directions, and you can design a two-way PT slab, which a lot of these slabs are. When I started out, I was like, okay, I don't know exactly, I had some classes, but it's different to try to implement that into design. You get done, and you're like, and then my supervisor that was working with me, you did a good job. That's pretty good. We'll get you onto another one. And like, well, this is easy. Well, and I'm not saying it's complicated. I mean, a trained professional can work through a PT slab design. Like I said, I feel I understand them very well. I'm not the most I don't have the greatest expertise in the post tens. There's a lot more experts in the field than me. I've had a lot of experience working on these slabs, and you do get somewhat comfortable with your experience level. But I can teach our new engineers to design PT slab, but it also is a design where it's not just something where we don't want to be per se software technicians and just push run. The joke about that in our office is you really have to think about what we're doing, because there's a lot of field conditions that sometimes you look at a plan and you're like, okay, I'm going to lay out my tendons, and then but we're going to put a crane block out for a tower crane here, and we put a big square hole in the slab here, and then we have a pore strip which we leave. I didn't really talk about those. The pore strips are basically 3-foot widths, 4-foot widths of slab throughout the area that we leave open after the tendons get stressed, and that slab is allowed to shrink, because a lot of times it'll happen if we have a long slab with, say, shear wall cores on the far ends. If we keep that slab locked together and then put that pre-stressing force into the slab, we're going to experience shrinkage, and that shrinkage will cause cracks. So we try to minimize concrete's going to crack. We try to keep, like I said, an uncracked section. So we try to lay out things like pore strips, and that's just, everyone does these differently, but it helps try to minimize the cracking. But we leave these strips open for anywhere from 30 days. It used to be longer, construction speed and so forth. They want to close them sooner. So at least 3 weeks, we let that concrete shrink, and then we pour them back.
So Ryan, something I didn't ask. What strength does the concrete have to reach before you stress it?
We typically like to see 3,000 PSI concrete when we're designing with a 5,000 PSI mix.
So are contractors trying to drive early strength concrete then?
They do. They want to, a lot of times, because they want to get the slab stressed, because with a PT slab, as soon as they get this slab stressed, they can pull their shoring out. They can start working. The trades can start working under the PT slab. They can start moving forward. They want to get the slab stressed and move on. And it's always the battle of, we want to wait. Concrete's green. It's very new. We get contractors who are like, well, we want to do it in 2 days. Well, we can get concrete strength, and it's that game. Well, you want 3,000 to drawing, say, I'm going to get 8,000 PSI concrete mix. In 4 hours, it's going to be 3,000 PSI. And we're like, just every company has their standards they like to use. And we have, our own, but we at least like to see a couple of days, because the concrete's very, very green.
Right.
It's very fresh, and so we don't want to have blowouts, because blowouts are a problem. If you stress this and something happens, we have maybe had a little void behind the tendon, the stressing heads or so forth. You're imposing this large pre-stressing force into the slab, and if something starts to slip, it can expand and blow. We call it blowouts, but you can have a blowout of a section of concrete. And so sometimes we're like, let's wait the extra day. I know you want to get this thing stressed, but usually we shoot for at least 3,000 PSI mix. And
okay.
And that's can be tested. They'll take extra samples and they'll test that. Then they'll let us know, hey, do you approve? Can we go ahead? And we've had good success with that.
So if I was a new engineer, I go out to a job site, they've got, all the shoring located for the slab. all the rebar in place. Let's say sequencing is irrelevant here. They have no PT in it. And you go out there as a young engineer, how would you be able to know for sure that that's a PT slab versus a non-PT slab? Like, what are the telling signs? What does the reinforcing look like that's different on a PT slab?
On a PT slab, we typically, to make these spans work, the post-tensioning is doing a lot of the work. It's helping to minimize the stress in the slab by this balancing that we talked about. We use a profile that causes an uplift to help lift up, and that's the dead load that's being imposed on, and the live load that's being imposed on the slab. So if this was a conventional reinforced slab, you would see probably top reinforcement, maybe a grid of reinforcement in the top of the slab. You'd see a heavy grid of reinforcement in the bottom of the slab. Whereas the post-tension slab, we have a minimal grid of reinforcement in the bottom layer of the slab, we could call it, and then switch is located about an inch off the bottom of the slab. And it could be a grid of number 4s at 48 or something like that. We're in a seismic region out here, so we have to also have diaphragm capacity. So sometimes we have a little tighter grid of reinforcement, but elsewhere we've worked throughout the country, and we've worked in projects where we're in the Midwest, and it's a very minimal layer of reinforcement. So either way, you'd see less reinforcement in the slab because those tendons are going to be in there to help do some of the work. That's the biggest thing, I think, when you first walk out. You're still going to have punching shear resistance. We use stud rails. It's real common to use at the columns. You'd still see that. But the biggest thing is the amount of reinforcement, of the conventional mild reinforcement that's in the slab.
What about around? I'm thinking like these tendons have to sweep around things, and then also like at their ends where you have some sort of compression block, that you're stressing through. Is there any additional bar there from preventing, a different thought of blowout or something like that? Do you see more reinforcing around those areas?
There is. As we were saying, with the reinforcement with a post-tension slab, you're going to have these tendons that are going to be profiled in both directions, or span in both directions across the slab. They run clear of the strab edge because we have to be able to grab on to that tendon and stress it. So that imposed pre-stressing force is imposed on the anchors. And so there's the dead end and there's the live ends we talked about, and that's going to squeeze on the slab. Well, that actually wants to split the slab apart. So if we get too many tendons together in groups, which we allow for like a banded direction group of tendons, we could have 30 or 40 tendons grouped together. You think about 30,000 pounds of force pulling on the middle of the slab, it wants to open that slab up. So we have reinforcement, bursting steel reinforcement, they call it. And there's extra reinforcement we do at the heads that helps confine that slab when we have a certain amount of tendons. And that rebar is just there. A lot of times it looks like U-bars. We'll have some straight bars. We have backup bars and things that's commonly shown in standard details from the Post-Tensioning Institute that they recommend for use in these type of situations. And it helps confine the slab, hold it together so it can handle those pre-stressing forces that are trying to basically split the slab apart. We have, obviously in a perfect world, we'd have just everything is orthogonal, square building, columns are all on perfect grids, no openings, but we wouldn't have elevators or stairs. So sometimes the tendons have to sweep around openings. They sweep around, say, an elevator or stair shaft, and so you have this kind of a sweep. And so, which it just moves horizontally in the slab. But now we go back to there's a imposed force in that tendon, and now it has a curve to it in the horizontal plane. So when you stress that, it wants to move horizontally through the slab thickness. And so we have also U-bars, hairpins that we'll put on the tendons to keep that lateral thrust, because say we sweep around an opening and then they stress these tendons, those tendons want to straighten out because you're putting all this force in there. We use those U-bars to help hold those tendons in the curve. Otherwise, they'll blow through the form and end up in our opening. And then they'll be straight because they want to straighten out to release that force.
Okay.
So there is extra reinforcement we have, but it's usually localized to anchors and specific situations, sweeps and things. So.
Okay, so moving from the technical aspect to more of the construction, field issues types of things, what's the most common mistake you see during construction of PT systems?
The biggest thing, well, based on your last question, is is reinforcement at the anchorages. We have special inspectors that come out and do third-party special inspectors that review rebar placement, the quantity of tendons, the profile of the tendons to make sure it matches the design intent. But there's also this added rebar at the stressing heads and the dead ends of the tendons. And there's times that gets missed. Well, we want to avoid slab blowouts at all costs. I've seen not it actively happen, but I've seen the aftermath of when this happens, and it's fixable, but we don't want that to happen. It could be an unsafe condition, and so we want to make sure the reinforcement that we have shown is installed. And so that's the biggest one. I'll go out and I'll look for the bursting steel that I call. I look for the U-bars and the backup bars at a group of stressing heads at the slab edge, and it'll be missing. So like, hey, you guys are missing all the extra reinforcement for the bundle of tendons. Oh yeah, sorry, we'll get it taken care of. Great. I looked for that. That's a big one. And then you talked earlier about trades and so forth and coordination. We'll see sleeves. There'll be plastic sleeves throughout the slab before they pour the concrete, trying to get ahead of the game, making sure they have enough sleeves so they can coordinate all of the MEP that goes through the building. Well, sometimes trades that aren't as familiar will put plastic sleeves right next to a stressing head. That's where the localized force is the greatest from that stressing head. We go and we pull on this with a hydraulic jack, 30,000 pounds of force. It can possibly, if the stressing head is close enough to that plastic sleeve, it can crush the sleeve and cause another blowout. And so then, one, the sleeve is no good anymore, and two, we have to repair the tendon. So we have to worry about plastic sleeves being located near the stressing heads.
That makes a lot of sense. How crucial is sequencing when stressing tendons, and what happens if it's not followed? And where my mind goes here is, do you stress from east to west, north to south? How do you dictate where you start stressing and how that's done?
Typically, the contractor and the PT supplier usually will decide on kind of what part of the slab region they want to stress at. But typically, we start with the distributed tendons, the ones that are spaced out more equally. We'll stress those first. Then we'll go to the banded direction. And then if we have beams, then we'll stress those beams. And that's kind of the practice that we like to follow. Sometimes they'll have, like I said, we have to have a special inspector come out, because when they have this hydraulic jack that clamps onto this tendon and pulls these tendons to a certain elongation. That's how we know we've achieved. They have a gauge pressure that shows how much force is being imposed on that tendon, but then they also have an elongation that they have to achieve, because they're going to pull so much, and as that tendon gets pulled, it's going to elongate and pull out through the edge of the slab. And the special inspector measures that elongation. And so when we achieve that, then they achieve the force that we want in the tendon, then they can anchor the tendon. They release it back into like a gripping anchor that clamps around the tendon and holds into the head that's cast into the concrete section. And so when they release that, then that force is imposed into the slab as we wanted. Then the special inspector marks on a list, gives us, say, this meets elongation, or it was out of tolerance. Hey, this thing pulled an extra inch or 2 inches or 3 inches, depending on how long the pull is. Once they're all done with stressing, we get this report, we review it and see, is that doesn't make sense? Is there a problem there? Did something happen? Hey, we broke a tendon pulling on it. Things happen in the field. And so we will review those, and then they can cut the tendons off. But sometimes with these jacks, they'll use these jacks they want to get done as well. And there's hundreds of tendons that need to stress, and somebody needs to measure them. They'll start on two sides of the slab, and they'll work together, or they'll work from different areas to try to finish all those distributed tendons. All right, let's work on all the banded tendons, and they'll work two directions, will work together just to try to get done in a certain timeline. So we've had that before, where you have so many tendons they can't get them stressed all in the same day. So
that makes a lot of sense. You'd mentioned you haven't seen a tendon failure in the field, but what's usually causing those to fail beyond someone core drilling a tendon?
Well, sometimes it's not real common in our area, but you can get where corrosion, the tendon can somehow moisture, something got into the anchor heads, rust, something. Sometimes you can end up with corrosion issues that can cause the reduction of the section of the tendon and cause the anchors to fail. the anchor on the edge of the slab it's like a cone shape, and it grips with like small teeth onto the cable. Sometimes over time, maybe there was grout, maybe there was concrete on that anchor may slip and let go. Drilling's the most common cause of tendons failing, but I haven't seen, obviously I've come out and seen the aftermath of a tendon, of someone drilling a tendon. Usually, sometimes it's funny because there is this imposed force on these tendons, and they drill one. Some guys say they don't even know. Other people have said that they hear when this thing lets go, it vibrates the floor because it's basically released that energy.
Yeah.
And those grout pockets that are in the end usually pop out because now that tendon is released, and so there's movement, and it usually will push that non-shrink grout pocket out, and you'll see that. And so you go out in the field, and if you see a grout pocket that's come out, usually something's happened with that tendon.
So another thing I think about, and this usually happens during construction from my experience, is MEP is never fully done until the building's built, and then there's still more to go even at that point. How do you handle detailing of penetrations through your slab when it's added later? I'm not thinking just core drilling. I'm thinking like big, large openings. How do you handle that when you're in construction and they say, hey, we actually need to add this opening here? Is that a pretty easy thing to throw into your design, your program? Is it, does it create a huge issue? What's like the scale of this?
It depends on the level of change in the field. Sometimes with experience, you can see something like, hey, we're going to add this sleeve. Okay, well, one sleeve, 3-inch diameter in the middle of the slab. I'm not worried about that.
Right.
Oh, we're going to add 10 sleeves for roof drains that come down next to the column right through the slab at the most critical location of punch and shear. So that becomes a problem. Like, so if it's something that severe, we'll come back to the office. I know they want to pour the slab, which usually, hey, it's the next day, get me an answer. So we come back, we'll analyze the slab for the additional sleeves, see if we can make it work safe for punch and shear. If it's something out in the middle of the slab, away from the columns, we'll still look at that because it's still not an opening, and we're losing cross section of slab. Like I said, if it's one sleeve or so forth, the relative change the slab is minor. But if it's, say, a 4-foot square opening, we can come back and also add that opening into our slab analysis and check and make sure that we don't have stress problems because of the reduced cross section for the tributary width of area, I guess. So we can accommodate that in the field depending on the level of change.
So even before that, let's say, how much coordination are you typically doing with MEP, like on a PT slab?
We try to coordinate. Most of the time, we usually get the sleeve locations, or not necessarily sleeve locations, but shaft locations,
right,
from the architect. That's usually architecturally driven. They have mechanical rooms, and here's all the electrical is going to come up through the building in this location. So usually we'll try to coordinate those locations with the architect, and then that gets shared with the MEP coordination. Coordination with MEP in the field does happen at times when we have to, things that were missed, things that were added to the building, maybe after permit. Hey, we need an extra, whatever we need. We need 5 runs of 4-inch sleeves going up through the slab. We can coordinate with them, but typically we try to get that stuff ahead of time, coordinated, located in the slab, so that way we don't have to do drilling later because of all the risks of hitting tendons.
Okay. So to wrap us up here, what are some questions or things that you think our listeners should know about PT that I haven't asked you or we haven't brought up yet?
I guess as far as advising a young structural engineer is mostly it would be to understand the fundamentals of PT. You know, we also just we want somebody who understands what they're working on. And so, I mean, that was kind of when I started. It's like, well, you're going to do some of this by hand, then show me you can do this. The biggest thing is just understanding like the basics of what you're trying to accomplish with post tensioning, the balancing of the dead load, and thinking about, okay, well, I need so much uplift in a long span. So really, I'm going to keep my tendons high at the columns, low at the midspan, and then get the most lift. But then, hey, we've got a 28-foot span here. Well, I can't use the same amount of lift in a 15-foot span, because then that slab will uplift and can possibly crack due to initial stresses because we have too much uplift. So it's kind of this balancing act. I always look at it kind of like a wave, like, okay, I need to be low here. Just visualizing what's actually what it's working with. I need to be low here, maybe not so low here. And then, oh, I'm at the cantilevered end. Maybe let's lower the profile a little bit just to think about what the post tension is going to do to the slab. That's how I look at it. I mean, I try to take kind of like just a basic approach of what is the post tensioning doing and how do I maximize its efficiency with my layout so we minimize the problems we see in the field.
I like that a lot. My last question here. What is one thing you wish you knew at the beginning of your career that it's taken you 20 years to say, learn? What is your advice to a brand new engineer in our industry? Don't do it.
That's the joke I was going to say is like, do you want to be an engineer? No, I love what I do. I think if the one thing I could recommend an engineer starting out is to be involved. See as how much you can be involved. There's young members groups around the area, structural engineer associations of different states. We have structural engineers of Oregon and Washington. They have get-togethers. Be out there, be willing to interact with these people, talk about that, and also be willing to go and do the extra effort of learning that sometimes, like, I went to school, I'm done, but like, it's not the most exciting sometimes, but to review the code and look through things or research, hey, there's a webinar or there's a conference or something to go to learn new things, because things change. They do. And I joke sometimes I'm the guy who still grabs my 2005 ACI, whatever, when I grab something, I know where that's in the section, but be willing to put yourself out there to learn the new trends in the industry and so forth. That's something that I think starting out, I wish I would have done more of that. And also be willing for the social interaction with your clients, because you're ultimately going to be working with architects. And I think there's a lot more of that than I realized when I first started is the interaction with who you're working with and having those relationships, because it is a relationship-based industry. I mean, it does come down to dollars and what's your fee and so forth. But if someone wants to work with you, they want to work with you. And so being comfortable with like, hey, let's have a social gathering. Let's talk about this. Let's do it to try to foster those relationships. Be willing to go out and do those things.
Well, great, Ryan. Thanks for being on the Structural Engineering Podcast. Really enjoyed our conversation today, and I hope our listeners learned a lot about PT.
Yeah, thank you for having me. It's been great, and hopefully some of the stuff I shared was beneficial. So thank you.